is such that we have a slight imperfection. So that means that one of the elements is slightly weaker, say 1%, than the other elements. So we load the bar until the moment that the weakest element fails. So this weakest element then goes on this branch. Now, since we must have stress continuity in the elements, the stress in this element must be the same as the stress in the weakest element. But since this element, the stronger element, has never been broken, the only way to arrive at this stress level is that it goes back here. So the total solution is m minus 1 times this solution plus 1 time this solution, and if you then elaborate that a bit, you get this solution. So the crucial point is you must have an imperfection and you must include stress continuity here. So, second part. What I'm now going to talk about is damage mechanics, also called in the French school the local approach to fracture, non-local approaches, gradient damage approaches, and how do you do this numerically. Now, the simplest possible damage model is just a bunch of bars. So here we have a wall. We force them all to be formed the same. They have a length L, and we have M bars. So the force is the sum of the stiffness of each bar times the displacement of each bar. Now we go to the case that we have some bars that we go to a case that we have a distribution in the strength of these bars. Some bars are a bit stronger than other bars. So we use the model of that each bar is brittle. So you go to a tensile strength of a bar and then go down to here. So the force at the moment that n bars of the m bars have broken is m minus n times stiffness, spring stiffness, times displacement. We can translate that into a continuum model, and we then say, okay, we here have our spring stiffness, we replace that by E times the cross dimension, and here we replace m minus n by 1 minus the ratio of n over m divided by the length. So we go to a stress-strain relation. And then we have the force equals our Young's modulus times our cross-section times our strain times 1 minus the ratio of broken bars. And this ratio of broken bars is the damage parameter. And clearly, when we have an intact system, n equals 0, and therefore omega or d, which is sometimes used, equals 0. So we have just the force equals 1 minus 0 times Young's modulus times A0 times epsilon. Or if we divide F by A0, we have our stress equals 1 minus omega times Young's modulus times the strain. And that is essentially the basis of every damage model you find in the literature. So the next thing is that we derive the tensile stiffness. So we here take our derivative of F. It's 1 minus omega times E times A0 times epsilon dot minus the derivative of omega with respect to epsilon times E times A0 times epsilon dot. So our stiffness of the system is 1 minus omega minus the omega, the epsilon times epsilon times E times A0. Now, again, we have this loading, unloading condition I talked about the previous lecture. Because suppose that we load and load and load until a number of bars have been broken. So omega has a certain value, and at that moment we start unloading. I mean, the bars will not unbreak again, they will not heal. So they will remain broken. So this omega has the role of a history parameter, which memorizes the amount of damage that has taken place in the past. So we have, in case of unloading, omega doesn't change. So the rate of omega is 0. But when we have loading, omega increases. So for our effective stress, which is essentially the force divided by the load carrying area A, rather than the original load carrying area A0, we have now 1 minus omega times Young's modulus times A0 times epsilon divided over A. Now you can generalize that to 3 dimensions, and in most general way you say my stress is equal to my stiffness, my secant stiffness, times my strain. And this can depend on a scalar, on a second order tensor, a fourth order tensor, whatever you want. And you want to make it complicated, you can. So for full anisotropy, you can do that in principle. Question is, of course, where the hell do you get the parameters from? How do you measure them? So, most cases, any damage model is a scalar-based damage model, and in that case, your secant stiffness depends on the degradation of Young's modulus and of Poisson's ratio. And in a further simplified version, usually it is assumed that Poisson's ratio doesn't change. So it's just Young's modulus which degrades. So this is the summary. Our stress-strain relation of damage models is we have a stress which is 1 minus the history variable omega, your damage parameter, times your elastic stiffness, your original elastic stiffness, times your strain. and your omega degrades. But you cannot degrade it directly. You have to incorporate, you have to allow for this possibility of loading, unloading. So you have to supplement this stress-strain relation by a loading-unloading condition, where you make a loading function which is dependent on the current strain, some scalar function, depending on your material, and the history. And you check the current strain with the largest value of epsilon tilde that has happened in the past. So the largest strain that has happened. Now, an example of that is this expression, which is often used for metals, and which is a half times the strain times the elastic strain, the elastic stiffness times the strain. Essentially a work expression. Now, if this indicates that you have unloading, you put your omega equal to the omega that was there before in the previous loading step. If omega indicates loading, which means that this one is bigger than this one, and therefore F is bigger than 0, in that case we have to update our omega according to the material function that is here. So the whole structure is, we have a one-to-one relation. We have a relation which expresses the stress as a function of omega and strain. We check, based on the strain, we compute an equivalent strain. The equivalent strain we feed into our loading condition. If F is smaller than 0, the history parameter remains unchanged. If it is bigger than 0, we update our omega. So here I've written out the algorithm, how you do that. So from your finite element or finite difference or whatever numerical approach you use, you compute always displacement increments in nodes. From that you get, usually an integration point, you get your strain increment. So you update your total strain as the strain that was left behind at the previous loading step, plus this increment which you've computed. Now you have your full strain tensor, and you compute your equivalent strain. For instance, using this function, or when you have another type of material, the function that is appropriate. You evaluate your loading function as the difference of your equivalent strain, which you just computed, and the history and kappa, which you have memorized. If F is greater or equal to 0, you have loading, and you update kappa. Else, if it's smaller than 0, you keep it to the old value. You update the damage variable, and that holds whatever you have done here, because it always has the right value here. So you compute, you have the right value for kappa here, so you can compute the right value for omega, loading or unloading, and then you'll compute the right stresses. It's 1 minus the updated omega times the elastic stiffness times your new strain. So this is essentially the algorithm you use to, in damage mechanics. Now you have to do a little bit more usually, and that is related to the fact that you not only have to compute your stresses from your strains, also you have to compute the displacements. You've always, in nonlinear processes, a double loop. You have a global equilibrium loop to update your displacements. Then you feed your updated displacements into your constitutive relation at integration points. So you transfer the variables, displacements in nodes, to strains in integration points. At these integration points, you compute the stresses. And from that, you compute the internal forces in the device. Then you check whether your internal forces are in equilibrium with the external forces loading on the structure. If the tolerance is sufficiently small, you say, I'm happy, I have sufficiently good equilibrium. If they are not happy, if they are not sufficiently close, you're not happy, and you use Newton's method, the Newton-Raphson method, to improve your estimate for your displacement increment. Now, in the Newton-Raphson method, you need the tangent stiffness matrix. So, how do you compute that? Well, you have your relation between stress and strain. You have to differentiate that to obtain a relation between stress rate and strain rate. So, when we are here, we differentiate this. This means that we first keep this, well, this one is a constant, and the elastic stiffness, but this is varying, and the strain is varying. So we use the chain rule, so we first differentiate this, keeping this constant, and then differentiate this, keeping this constant. So here we have 1 minus omega times d times the strain rate, minus the derivative of this is minus omega dot times d, e times epsilon. And now we have to use the chain rule to compute omega dot. Omega dot depends on the history parameter. And the history parameter depends on your equivalent strain. And your equivalent strain depends on your total strain tensor times the strain rate. And you see, this is a scalar, this is a scalar, this is a scalar, and this is doubly contracted. So it's also a scalar. Now, if we have loading, well, this you can always compute. This is an interesting model. Because, look here, if you have, if we have loading, this equals 1. If we have loading, look here, this is 0, so this is equal to this, and therefore the derivatives are also. If we then, therefore, if we do d epsilon tilde, d kappa, that's therefore equal to 1. However, if we have unloading, then it's not defined, so the derivative becomes equal to 0. So, if we have loading, this is 1. If we have unloading, this becomes 0. And the whole term falls out. That's not strange, because if we have unloading, we go back to the origin in a secant branch. And this 1 minus omega times dE is just the secant stiffness at this point. Yes?
Please go back, way back.
Sorry?
One slide back. One more. Yeah. So F will be 0 during unloading.
F is 0 under unloading.
And then this derivative will be 1.
Sorry?
The derivative which you said, del kappa by del epsilon.
I mean, here 0, then you have 0 is E epsilon tilde minus kappa.
Yeah.
And by implicit differentiation,
Yeah, it's 1.
you have the epsilon d kappa equals 1.
But for unloading.
For unloading, it's undefined. Unloading, this is smaller than 0. So you don't have an equality sign here. You have an inequality. A strict inequality. So you cannot define it. I mean, mathematically, you can do that. You have to work with a concept which is known as subdifferentials. So you can do it properly, but that goes quite a bit into functional analysis. But let's say, in an engineering sense, it's an inequality here. There's no relation, they are not equal, and therefore the derivative by implicit differentiation becomes 0. So for loading, you have the omega, the kappa, the epsilon tilde, the epsilon times epsilon dot. For unloading, this whole term cancels, and therefore you only have this term, which is essentially the secant difference. 1 minus omega times dE is the secant difference. You have here, you go up here, then down here, or somewhere here, and then you go down in a secant branch to the origin. So, substituting this into here, you get 1 minus omega dE minus the omega d kappa, the epsilon tilde, times dE times epsilon, outer product times the epsilon tilde, the epsilon. Double contracted to the string. Now, what you see is that already for this very simple damage model, and it's essentially simple because we started just by a bunch of parallel strands, we get an expression which becomes pretty complicated, and to my horror, is non-symmetric except for some special cases. Because this times this is unsymmetric. It only becomes symmetric when you choose epsilon tilde as this. Because in that case, if you substitute that into here, you get dE times epsilon, which is the same as dE times epsilon, and then you have a symmetric expression. So, but that's a special case. So in that special case, you get, as I said, dE double contracted to epsilon, cross product times this, and that is easy. So that was a simple bit. Now we go to the non-simple bit, the non-local damage mechanics. And I told you that damage mechanics becomes ill-posed as soon as this expression times a normal vector times a normal vector, and then the determinant, so the acoustic tensor of this expression vanishes. And then we get all the problems with mesh dependence, which are plaguing often damage calculations. So to solve that, we can say, okay, we don't make the stress in a point depending on the strain and the strain history in that point only, but we also make it dependent on a finite neighborhood. So we replace this loading function, which is a local loading function, by a non-local loading function, where instead of deriving this epsilon tilde directly from the local strain, we compute an epsilon bar, which is the volume average over a finite neighborhood of all epsilon tildes. So here we have our epsilon tilde. We multiply it by a weighting function. I mean, obviously, nearby strains are more important than far away strains, and you can use a Green's function, you can use a Gaussian function, a triangle function, whatever. You have to normalize it by the integral of the weighting function, of course, in order to get back the strain, in order that you don't increase the strain. So you can do this integral. You can then substitute this epsilon bar into the loading function. And you see such an example. This is a Gaussian function. And you get something that is working. Now, what you see is such a weighting function always contains a measure of length. This is a typical thing. This LC, which comes here back. That is the amount over which you spread. And obviously, when LC is larger, you spread it over a larger area, and long-range forces, long-range influences are more important. Physically, that translates into that your crack band zone, the width of your crack band, for instance, if you have a number of microcracks, or your fracture process zone becomes larger. This L is directly related to the length of your fracture process zone when you are computing, for instance, quasi-brittle materials. An alternative, which you also see sometimes, is that you don't average epsilon tilde, but you average the history parameter. You do exactly the same then, and then define a k bar, which is 1 over the 1 over psi averaging function times kappa integrated over the volume. Computationally, this is a bit easier. People have argued that it is mathematically, physically a bit better. Now, how do you do this? Pretty much along the previous lines. So we compute the strain increment from our displacements. We update the strain. We compute our local equivalent strain as a function of our local strain. We compute a non-local strain, and here you replace the integral by a finite sum. Here with weight function, the weight vector times this value times your strain there times the volume. I mean, you have to discretize that. Then you do exactly the same. You feed this in your loading function instead of epsilon tilde. You check it, you update kappa or don't update it. You compute omega and you compute your stress. So from there it runs exactly the same. So the interference is quite small in fact. Now there are some computationally some nastiness things. One thing is that in principle such functions are unbounded. I mean, they unbounded in the sense that they become small, but never completely zero. You can cut off it at some point, but even then, they increase the bendedness of your stiffness matrix enormously, because there is an influence between this point and this point. So that's not nice. Even worse, even if you manage to keep a damage formulation that is symmetric, this will destroy it. So an integral formulation gives you rise to very nasty stiffness formulations which are not symmetric. So what we have done is we have come up with some approximations in the sense of you can develop, for instance, this integral expression in a Taylor series. And then you make it the local one, and then when you develop it on basis of such a Gaussian function, you get first the Laplacian, then the fourth order expression, and so on. This is still a bit nasty. Why? Well, here we have at some point the second derivative of the Laplacian. And to compute derivatives accurately is a hell of a task. So you can manipulate this a little bit, and you can say, okay, we differentiate left-hand side and right-hand side twice, and then we get a second order term here. We then move that to the right-hand side, and we obtain something like this. So we get the Laplacian and the fourth derivative on the left-hand side rather than on the epsilon tilde. So epsilon bar is our unknown, is our global variable, and epsilon tilde is our local variable. Now, this is much nicer than this, and that seems strange. But I will tell you, explain. But before I explain you, I will tell you a little bit about the difficulties that hamper all these higher order models. And that's the boundary conditions. Again, we always tell our students, beware of the boundary conditions. Obviously, when you go to an integral formulation or a higher order formulation, gradients, you need additional boundary conditions. And you have to do something else additional on the boundary. And for instance, in here, for this gradient model, we also have to impose something for this epsilon bar on the boundary. So we either have to prescribe it, or we have to assume a natural boundary condition. Now, in practice, it's not such a big issue, because according to the 7-up principle, these kind of things have short-range influences. So unless your problems are close to the boundary, they will not have much influence. But it is an issue and you have to be aware of it. There's no good solution available. Now, you have some alternatives. You can expand, of course, also kappa bar, and since kappa omega is a direct function of kappa bar, you can also expand omega. So, how do you do this now? Now, you compute the strain increment and the non-local strain increment. How we exactly compute this one, I will reveal in a moment. We update both the strain increment and this non-local equivalent strain increment, strain. We evaluate the loading function and then do the usual thing. If it's bigger, we update, else if not. And we evaluate our damage variable and compute our new stresses. Now, why is this implicit gradient function damage formulation so nice? Because we can do mixed finite element formulation. We can interpolate our displacement, but we can also interpolate our additional strain field. And usually we will do that with different interpolation polynomials. So capital H is different from capital H bar, because strains are usually an order lower than displacements. So you must adapt your interpolations from it. You have the interpolation of your test functions in a similar way, and you obtain your equilibrium equation, usually like here, but an additional one for this averaging equation. And essentially what we have done is we have taken this equation with only this term and this term. We have integrated this by parts, and then you arrive at this for epsilon bar, and this for the additional term, which is the gradient of epsilon bar. So you have now two equations which are coupled. Because if you elaborate it, you get here 1 minus omega times your stiffness. But you can get also an additional term of the second part of the stiffness matrix, which is the derivative of omega with respect to kappa. So that comes here. And from the second equation you get also different contributions. This one, which comes here, and this one, which comes here. And this one, when you differentiate it, you get then this one. Now, the nice thing is, the system is symmetric. It's nicely coupled, it works easily. And the only disturbing thing is that this thing may be not the same as this, but that was in the standard damage formulation. So we cannot improve something which was a problem already. Now, does this work? Yes, this works very nicely, in fact. So this is the case, again, of a bar with a small imperfection. So here we load it. We have a cross-section here over 10 millimeters, which is 1 square millimeter reduced. And when you then refine mesh, you do see that you get convergence to a physically meaningful solution, because the area under this curve is finite and therefore shows energy dissipation. This is another case where here you see that it's a single astronaut specimen here you have a loading, sorry, here you have two loadings, here you have 2 points, there's a pre-notch here, and the crack starts propagating from here to here, and later from here upwards. And you see that these damaged zones are properly reproduced independent of finite element discretizations. There is some issue though, and that is when you here look at this 3-point bending test, you see that the damage zone not only propagates, so here you have a 3-point bending, a load here supports here and here, not only propagates but also broadens. And this is something that is more than or not really physical, and we will come back how to solve that later. In effect, one of the solutions that have been proposed is make this length scale dependent on the amount of damage. So when you have progressive damage, the length scale should vanish, should become smaller. And then you can reduce it.